Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 85. Now, in the previous lecture, I told you that we are done with this course. So, in this lecture, I just wanted to give you the perspective emerging from this course, the need for this course. I already mentioned it briefly in lecture 1, but hey, lecture 1 was before you went through the content. But now that you've been through the content, right? I mean, quite a significant amount of lectures and material, I think the perspective would be fresher now. So the perspective, and it's also in the form of an epilogue. That is some time to introspect and what you learned, how you learned, what you should learn more, etc., etc. Okay, so in the first 5 lectures, that is from lectures 1 to 5, the broad module that we were discussing was on the topic of introduction to astrochemistry. For example, how this field, astrochemistry could be very generally defined as the behavior of molecules in space, and how that leads to not just new knowledge about chemistry on space, but also about how we can reinterpret and understand, and develop further our repertoire of chemical intuition. So that's the idea of introduction to astrochemistry. This was followed by explaining to you what the interstellar medium meant. That is the ISM, a phrase that we use so often in this course, and how the chemistry and the physical conditions in the ISM is so different vis-a-vis what is known on Earth. So these were the first 10 lectures. By the way, each lecture is approximately 30 minutes. And then we had our first 4 tutorial sessions where we solved for assorted problems in astrochemistry. And yet another objective of the tutorials were to clarify some points which were not well made in the lectures, or to clear some questions or doubts, and also to rectify blatant mistakes which I made. Okay, so those were the purposes of the tutorials, and that is followed by, in lectures 15 to 18, we were discussing about the molecules in ISM. So this is astrochemistry, right? So what are the molecules that have been detected in space? And we were discussing about the different types of molecules, ranging from the very small ones to somewhat bigger ones such as C70, etc., etc. So this was the first introduction to the course of the first 18 lectures. Then in lectures 19 and 20, we finally got to the topic of how do we detect atoms in space. In other words, I've been telling you all along in the first 18 lectures that, hey, there is something in space, but what is the basis for it? What is the logic behind me claiming from Earth that some molecules have been detected way beyond my physical abilities, right, in the outer space, way beyond my reach, right, in the outer space. So we saw how the experimental science was tremendously helpful in detecting atoms in space. And by the way, this is nothing modern. It goes back all the way to 1800s. Okay. Now this was followed by, as part of detecting molecules, we understood that one key concept was what is called as a spectral signal. So now, molecules on space and molecules on Earth also give us spectral signals. So what do I mean by a spectral signal, and what causes them? That led us to a discussion on the fundamental aspects, the fundamental types of motion that a molecule undergoes. In other words, we were dealing with this highly applied and interdisciplinary science of astrochemistry, and as part of it, we needed to understand the fundamental aspects of physics and chemistry, the basics of fundamental sciences. In other words, one could do well in an interdisciplinary course if only the basics were thorough. I'll repeat this point again and again in this lecture. Okay, so we started off our discourse about the fundamental aspects of molecular motions, and then in lectures 23 and 24, we had 2 tutorials wherein specific aspects of molecular rotations and vibrations were discussed. This was followed by lectures 27 and 28, wherein we were actively engaged in our pursuit of how molecules were detected, going beyond atoms, how molecules could also be detected in space. Then the overarching theme of lectures 19, starting from lecture 19 all the way to lecture 28, was that we needed to understand the interaction of light with matter to eventually detect molecules. So therefore, in the context of astrochemistry, what was light? Well, we have some rudimentary understanding from our high school, but at a collegiate level, at the undergraduate level, do we actually understand what light was and what a beautiful dichotomy it presented? So as part of it, we understood the wave particle nature of light and some aspects of black body radiation, etc. In I think 1 or 2 lectures in the module light and astrochemistry. This was followed by what does light interact with? Matter, right? So we also had to understand what matter meant in the context of astrochemistry, and that it was not like a chalk piece of a ball. These were quantum mechanical entities which had their own special properties, including wave particle duality. So matter and astrochemistry was introduced, right? And that gave rise to the opportunity for us to understand very basic quantum mechanics as relevant to astrochemistry. So this was done through lectures 33 to 36. So why did we, take up a study on quantum mechanics, devote a few lectures on quantum mechanics to astrochemistry? Well, because both light and matter, right, they are both quantum mechanical in nature. So that is how we know that there are molecules in space, and that is how we study the molecules in space, comfortably being here on Earth. Okay, so this tells us the significance of connecting the basics once again to study this highly interdisciplinary and applied science of astrochemistry. All right, so around lecture 36, we had introduced quantum mechanics, and this was followed by a few tutorial sessions wherein I emphasized to you the significance of units and dimensions and some aspects of quantum mechanics and quantum chemistry. And we also looked at some assorted problems in astrochemistry. And I also told you how a theoretical concept such as the black body radiation, right, could help us in even determining the temperature of a star. So these were the tutorials, this was the content that we looked into these tutorials in lectures 37 to 40. This was followed by, in lectures 41 to 44, having understood the nature of light in astrochemistry and the nature of matter in astrochemistry, we studied the interaction of light with matter as relevant to astrochemistry. In other words, we started discussing about the Einstein coefficients, the concepts of spontaneous emission, spontaneous absorption, simulated emission, etc., and how they're all going to give us information relevant to astrochemistry. So this was 41 to 44. Then what we did was, ultimately, why do we study the interaction of light with matter? It is to understand the only output that we get from the molecules in outer space, in the interstellar medium. That is the spectral line, right? So ultimately, we had to understand the significance of the spectral lines in astrochemistry. For example, we call it a line, but the line might have a finite width, right? And what does that arise due to, etc. I think somewhere around this time, between lectures 41 to 48, I also gave you a qualitative introduction to the notion of transition dipole moment, right? And the dipole moment integral, and how that is important in interpreting the spectral lines. So this was followed by three or four tutorial sessions in lectures 49 to 52, wherein we were discussing about local thermal equilibrium, a phrase we used often in this course, and how the Boltzmann distribution could be derived. Okay, and this was also followed by the significance of this concept called as the partition function, which found widespread use later on, right? For example, in the Saha equation and all those aspects. So these were the tutorials which once again emphasized on the connection of the basic science to astrochemistry. This was followed by approximately quite a few lectures, from lectures 53 to 60, wherein we were talking about spectroscopy for astrochemistry. Part of the bad handwriting, as always. Okay, right? So what I've written here is spectroscopy for astrochemistry, where we discussed in some detail the notions of microwave spectroscopy, aka rotational spectroscopy, vibrational spectroscopy, and how they're all relevant, to detect molecules in space. Then In lecture 61 to 64, I was briefly talking to you about the rotational spectroscopy of polyatomic molecules. I haven't mentioned it here, and the significance of moments of inertia. And also was talking to you about term symbols for atoms. We did not have the time to go through the term symbols for molecules. Then I briefly was also talking to you about selection rules as relevant to the rotational, vibrational, and electronic spectroscopy for the atomic systems. For molecular systems, we needed some more theoretical foundation, but that can be learned in a different course titled Molecular Spectroscopy itself. So this is how we, all the way, and starting from approximately lectures 21 or 22, or lecture 20 itself, where we saw that it is through a spectral line that molecules are detected in space. We learned about the relevance of spectroscopy by around lecture 60. This was followed by some related tutorials in lecture 61 to 64, as I just told you now. Now, then in lecture 65 to 68, we were also talking about some important aspects of astronomy as relevant for astrochemistry, such as, for example, if I'm correct, we were discussing about the merits and demerits of observing molecules from Earth versus creating space stations and then making our measurements from there. Such concepts were discussed. This was just a brief introduction to astronomy for astrochemistry. Astronomy is an ocean of its own. Please note that point. In fact, two aspects of astronomy which I wanted to cover but I did not cover are the notions of radio interferometry and radio telescopy. For example, see, interferometry is a beautiful science wherein you have a single beam of light, you let it interfere, you form various patterns, and then you analyze the patterns to actually detect molecules. We did not have the time for it, but that's okay. Yet another related aspect I could not teach, somewhere in this context, starting from light matter interaction to astronomy, was the concept of radiative transfer. I wanted to just, under conditions of local thermal equilibrium, wanted to give you one or two examples of how radiation transfers across different molecular clouds and how that information could be used to get the properties of these molecular clouds. But that's okay, we cannot have it all in an undergraduate course. But please note that just get to know the names so that in your future pursuit you can study more about radiative transfer and also about the details of interferometry and radio telescopy. So this was an introduction to astronomy for astrochemistry. Then in lectures 69 to 72, we finally were discussing about chemical reactions which are relevant to forming the molecules in space. One key idea to emerge from these lectures, molecules that are detected in space, that's a fact. It's an established fact that molecules are detected in space. But the chemical reactions which they are occurring, they are our proposals. Of course, we do it with a lot of care and attention. So the reactions we propose are going to be most likely to be meaningful, but no one can definitively say that, oh, this is the reaction which leads to the formation of this molecule. That's an important idea to note. So then after this, we had some more tutorials in lecture 73 and 74, where we were discussing about some more astronomical aspects. In particular, the concepts of line of sight. How do we get the ideas such as column density and number density, and also about spatial versus spectral resolution. Okay, so these were some astronomical aspects. Then from lecture 75 to 81, we were discussing about, it's very badly written here, please bear with me, the chemistry of meteors, comets, and planets. Meteorites, comets, and planets. So between lecture 75 to 81, we were discussing about how beyond the ISM, right, all the material that got accreted, probably going back to lectures 1 to 5 itself, I told you that meteorites, asteroids, etc. could also be formed. We were discussing qualitatively a lot of their chemistry. Then finally, from lectures 82 to 84, we were discussing about prebiotic chemistry. In other words, the chemistry that may have plausibly been responsible for the origin of life on Earth, and also connected it with the highly interesting area called as astrobiology. I only mentioned in fleeting about astrobiology, also noting that while we discussed the chemistry of meteorites, comets, and planets, they're all associated with the area called as astrogeology. Just get to know the phrases, okay? So with that, we covered various topics, and throughout the course, the focus was on connecting the fundamental sciences with the applied sciences, because progress in applied science cannot be made without a proper understanding of the fundamental sciences. This is the overall list of modules and the logic behind why a particular sequence was followed, okay, right? And also the importance of understanding basics to actually do anything in an applied science. I apologize if I repeat this aspect again and again, but that is quite intentionally so, because without the fundamentals, well, any applied science may not progress much. Okay, on that note, I also want to talk to you about a few aspects, a few more aspects to possibly come out of this course. So the next point is, what after this course? Okay, I've been patiently listening to a series of 84 half-hour lectures, and also bearing with the handwriting, right? What next? Well, the idea would be that after this lecture, each of the modules could be a specialized master's course. Please note the point. Each module, a module comprises of multiple lectures, okay, right? A series of lectures is a specialized master's course. So depending on what aspect of astrochemistry you are most interested in, right? For example, if you're interested in the chemistry of meteorites, you may want to pursue more about look up and then pursue more about these aspects. Or if you're interested in astrobiology or prebiotic chemistry, you start off by knowing some things, right? Just a few tidbits of understanding at the undergraduate level, and take it from there on. So then you could accordingly choose your courses from these modules and specialize in any of these areas. All of them, of course, have to come together to understand the bigger picture in astrochemistry. So this is one thing. And the other thing is, I think you are now somewhat equipped, okay? You're somewhat equipped to actually start reading. I'll carefully use this phrase. You're carefully equipped to start reading original research articles in astrochemistry, somewhat a little bit of astrophysics and astronomy also. In astrochem majorly, somewhat astrophys and astronomy. Noting that you may also understand a few phrases in astrogeology and astrobiology. Okay, but the point is, you can now start looking at original papers, and some of the terms will begin to make sense. How to make complete sense of it? Well, for starters, come again and focus on any of these modules that are needed. And after that, go deep into every single equation, the assumptions made, and the limitations of the methods proposed. That's very important. So you can choose your own specialization. If you're a master, if you want to pursue, some sort of a master's program related to related to science of the space, or if you want to do research itself, you want to be a PhD student, you're actually equipped to start reading the papers. I'm again emphasizing, I've not given you the skill sets to completely understand the paper. No undergraduate course could. But with the skill sets obtained, you can start, and then it shall more likely appear less hazy than being completely out of sorts. Okay, so these are the points about what immediately after this course. Next, I want to talk to you about some aspects of this course. So the first point is that the emphasis in this course was not just to, just spew out jargons and tell you about some terms in astrochemistry. The single major objective in this course is to emphasize that any applied science is built on foundations based on basic sciences. In other words, foundations of astrochemistry are deeply rooted in physics and chemistry, and of course quite a bit of geology and biology, but they come much later. So the physics and chemistry are very important. A lot of, not when I say physics and chemistry, a lot of branches come together, as I have been telling all along in this course. So please pay attention to this aspect, that don't merely be guiled into thinking that it's an applied science and without knowing the basics I can make sufficient progress. That is not going to happen. I apologize for being rather blunt, but this is the heart of the matter. It is that is in fact why whenever possible, I always explain the limitations of the methods we were using. Okay, right? Explain the limitations. And whenever I gave an example of an equation, I told you, I didn't simply give you an equation. I told you what is the unknown and what is the known in these equations. Because oftentimes at the undergraduate level, it's easy to forget that, oh, you can get something from an equation, but how do you solve the equation? You solve the equation by first of all knowing what the knowns are and what the unknown is. This is something very important as you move forward in your academic journey, especially in the sciences. Okay, so explain the limitations and clearly state the knowns and the unknowns. So this was page 5. I'll continue in page 6. The next thing is, I've intentionally used only blackboard and chalk, so that you get more time to retain the content that I'm presenting in the lectures. The drawback, of course, is that you have to bear with my handwriting, but to overcome that, whatever I write, and especially if it is not clear to me, I tell you folks that, hey, this is what I've written here. Please note that point. Okay, I'm not writing it because it's just a cosmetic thing. The next thing is, this is important. I mean, whenever there have been mistakes or clarifications required, I've always tried to include them in tutorials. So mistakes and clarifications provided in many tutorials and also some lectures themselves. So beyond this also, for example, if you were to take this course in SwayamPrabha, and then in the video we shall be having a note, where you shall see the specific note. For example, oh, mistake made. The correction is as follows. Or you can also, if say for example I made a mistake and corrected in a subsequent lecture, I direct you to the subsequent lecture in that video. Please note this. Okay. But beyond all this, note some mistakes could go undetected. Okay, despite our best efforts. Could go undetected, in which case, if you feel that there is something amiss or something is not clear, please do write to me, right? At Raghurama at labs.iitirupati.ac.in. So I'll repeat it because the handwriting is bad. Raghurama at labs, LABS, dot IIT TIRUPATI, IISCR-TIRUPATI.ac.in. So please write and I will clarify. So this was point D. And the last point is, note that these 2 points, the next 2 points are going to be in the form of part suggestion, part advice, but bear with them. Okay, it is that. See, learning is both linear and non-linear. That is to say, while we progress our discourse in any topic, we can go from point A to point B. We think it's linear. But hey, it's only after some time that you realize that there are lots of knowledge gaps. Okay, this non-linearity arises due to knowledge gaps. So please be aware that even after this course, there will be a lot of knowledge gaps. You can get them cleared through various sources, including writing to me. All right, including by writing to me. So note that knowledge gaps will be there after this course also. So, I mean, you can always write to me and I'll help you. If not, if I cannot deal with it, I'll at least point you out to the right resource as to how this knowledge gap could be made smaller and smaller. All right. So this was the content on some aspects of this course. Lastly, I want to end by mentioning to you about the various aspects of where the space industry, and in particular the Indian space research scenario, where is it going towards, and what is in it for the next generation of students. So this recording is being done approximately in March or April 2024. While we speak, globally, the space sector is poised for a growth of approximately $1 trillion. For, a McKinsey, which is a consulting company, McKinsey report, which I read on 29th March 2024. I mean, I do give dates, okay, but it's okay. But please note it. So while we record this lecture, space is a very exciting area going up forward. So knowledge related to space, which is again founded firmly on fundamental physics and chemistry, okay, and other sciences, right? It's important. So the more you know about the various aspects of space, including the chemistry, there is a lot to benefit and learn. This is the global scenario. Especially when it comes to the Indian scenario, we are at a very exciting time. So specifically to India, right? You may also, by the way, read about this report. You may just Google it and find this report and read more about it. Now, specifically in India, our space agencies, notably ISRO, has made us proud by undertaking a lot of, positive measures. They include Mangalyaan, Chandrayaan, and before that, launching a lot of satellites. Indian space research is something, it's a force to reckon with, okay? Beyond, what's already been done, in the future, they also have the various Mangalyaan 2, which is the mission to go to Mars again. And you also have Shukrayaan 1, which is the mission to go to Venus. And then we, of course, have this amazing program of Gaganyaan, where, we want to send astronauts to space. And lastly, there is also this Indian endeavor to build a space station sort of thing, to build a space. I'm, of course, excluding some of the other missions, such as Aditya, etc., which are already in vogue. So these are some planned missions, missions planned for the future. And notice that all of this also has a chemistry component. All of this has a chemistry component. And by learning about molecules in space, one can contribute to all of these missions in various ways. And not just that, we can also ask a very big And perhaps not easy to answer question. Can we also find life in on systems beyond Earth? So these are the various aspects about this course, and I hope that you found it useful. For any other interest, please do reach out to me in this email ID. Thank you so much. Have a good day.